Crossan. Elizabeth unfortunately couldn't make it, and so I was asked to fill in, which I'm happy to do, although it's too bad we can't have Elizabeth here. And what I'll be talking about has nothing to do with the topic of her talk, so rather this will be essentially, for those of you who were at AQC last year, this will be an update on a result that I presented there. This is work funded under QEO and is done in collaboration with a former graduate student of mine, Anurag Mishra, a current graduate student, Adam Pearson, and Itai Chen, who's here. Okay, so for those who were at the banquet yesterday, Wolfgang was talking about the doom that is overtaking quantum annealing. So I'll contribute to that spirit of pessimism, but I hope to also counter that with some hope. So this is part one. This is my favorite picture of a control error. That's what happens when you have analog controls and they misfunction. So what is the problem with quantum annealing? What is one of the problems, or perhaps the main problem for practical implementation? It has to do with the analog nature of control errors. As opposed to the circuit model, where we have a full-fledged theory of quantum error correction, which relies on the digitization of control errors. It's fundamental for fault tolerance, the accuracy threshold theorem. We don't have such a thing in quantum annealing. Right? In quantum annealing, we're doing analog control, and therefore we have analog control errors, and those are a big problem, as I'll try to argue in a moment. But I'll say that there is a caveat to this, which is there are techniques which we heard about, for example, in Birgit Whaley's talk on Tuesday, to introduce some form of error discretization, somewhat analogous to what is done in digitized quantum error correction in the circuit model. But I'll set that aside, and I'll define what I mean by a control error. So here's our favorite quantum annealing Hamiltonian. Whether we modify it and do something like reverse annealing doesn't matter. The point is, I will focus on the control errors in this final Hamiltonian, the problem Hamiltonian. And the tilde denotes that it is the implemented Hamiltonian, which you can think of as a sum of the intended ideal Hamiltonian plus some error term. Right? So this is the good, this is the bad. The bad is some control error on the sigma z's and another control error on the sigma z terms. And let's say that these errors are Gaussian distributed with some standard deviation eta. And I will completely ignore control errors, which are certainly there as well on the transits field term. Those will just make matters worse. So this type of error model has been recognized for more than a decade, going as far back at least as a paper by Katzgraber and Korzakala in 2007, who referred to this as disorder chaos. And then more recently, this has been called J-chaos or analog errors. And fundamentally, what is the problem with this type of error? The problem is that even if you had a otherwise perfectly working quantum annealer, let's say the only trouble was that it had these control errors, if it worked perfectly, it would solve the minimization problem associated with H tilde and not with H, right? So it would be providing you the right answer to the wrong problem. Okay, that's not good. So how bad is that? Well, in this nice recent paper by Tamim Albash, Victor Martin Mayor, and Itai Han, they analyzed this and showed, based on a purely classical analysis, so focusing purely on the Ising Hamiltonian, not on the transits field term, they showed the following result. Essentially, the problem is exponentially bad. The probability that at least one ground state of the intended Hamiltonian, the one you wish to solve, remains the ground state of the implemented Hamiltonian, the one you got, that probability is exponentially small in the problem size and also in the standard deviation of the noise. Not quite, it's up to some power alpha, where alpha depends on the Ising model. Okay, so the probability you're going to get the right answer from the wrong Hamiltonian is exponentially small. For later, of course, for chimera, n is 8 times L squared, where L squared is the number of unit cells. Okay, so we decided to test this on randomizing problems. So consider randomizing problems with zero local field, and Jij is chosen from this set. And so what we did was, rather than just rely on the intrinsic control noise, which for the D-wave 2x at USC has standard deviation of 3%, we decided to add artificial coupler noise. So basically, instead of sending the desired Hamiltonian, we deliberately added delta J's to the Hamiltonian that we programmed. And we ran that for different values of the standard deviation of the noise eta, and also for different sizes. We ran it up to the maximum size 12 on the USC-based 2x, and up to size 16 on the NASA-based 2000Q machine. So here's a glimpse of the kind of thing you find. So this is plotted as a correlation plot, where every data point here is a single random instance. In this case, for eta equals 0, so no added noise, versus eta equals 15%. So what you see for different sizes, displayed here from 7 by 7 to 15 by 15 unit cells. First of all, you see that when eta equals 0, these instances are generally solved with some non-zero success probability, although it declines as a function of size. Again, here is L equals 7, over here is L equals 15. But the same instances, when you add 15% noise, basically they're almost never solved. Right? So they lie on the zero probability axis. So adding this noise makes things a lot worse, as expected. So let's be a bit more precise about what we might expect from a classical solver subject to the same kind of noise. Right? What is the kind of scaling, the worst case scaling we can expect? Well, first of all, if you're given an Ising Hamiltonian on chimera, you can always solve these problems deterministically, given enough time, right? And I believe it was Vicky Choi who first showed an explicit scaling result for this using dynamic programming. And the result is that with dynamic programming, you would need a time scaling like 2 to the 4 L. L, again, is the number of unit cells along one axis, to exactly solve any given on chimera H tilde. But now again, remember the result that I already quoted from this paper, the probability that the given H tilde has a ground state that is the ground state of the desired H without a tilde, that is exponentially small. Right? So the time that it would take you to deterministically solve and find the ground state that you actually wanted, the one that belongs here, is the deterministic time, 2 to the 4L, divided by the probability that you actually had the right ground state to begin with. So the classical upper bound on the time to solution basically scales like e to the L squared. Okay, so e to the L squared, you never have to work harder than e to the L squared classically. So what do we do? What do we get when we put this on a D-wave 2000Q or D-wave 2x? Here is the time to solution, log of time to solution, rescaled basically after finite size scaling analysis for different values of eta, different problem sizes. And here is a curve that does a pretty good job, except for some outliers at really large sizes, because there the problem is almost never solved. And what we find, disappointingly, is that the scaling here, L to the D is a little larger than 2. But remember that the classical upper bound, the worst amount of time you'd have to spend classically goes like L squared, right? D equals 2. Classically, you would never have to work harder than D squared. So this is the doom, right? Control errors are really, really screwing things up. Okay, I hope you're sufficiently depressed. Now, there's hope. Okay, and the hope, of course, comes by introducing some kind of error suppression and error correction. So the scheme that I want to describe briefly, many of you have heard it more than once, I believe, for dealing with this problem is the quantum annealing correction scheme. And this is based on the idea of introducing repetition code along with an energy penalty. So very briefly, what we do is we take a repetition code of one logical qubit into n physical qubits, and we encode the Ising Hamiltonian. So this is the encoding scheme. Logical Z operators are just the sums of physical Z's, and logical ZZ operators are the sums of pairwise physical Z's. So that's the encoding. This turns out to be a repetition code encoding. Then the next thing is we add a penalty qubit. This is one way of doing the quantum annealing correction scheme, the simplest way. Of course, this is driven by the chimera cell structure. So we take these 3 physical qubits, which we think of as a logical qubit. We couple them ferromagnetically to a penalty qubit, and the penalty qubit enforces an alignment of these 3 physical qubits. So that's the penalty term. It's a ferromagnetic term that we can add. And then we combine these two. So you have your encoded Hamiltonian, and you have the penalty Hamiltonian with some penalty strength that needs to be optimized, gamma. So that's the fully encoded penalized Hamiltonian. And then we run quantum annealing. So in other words, we just add a transverse field and let the thing run. And at the end, we decode each one of the logical qubits. We decode by majority vote, simply picking the majority among 3. So this idea was inspired by the original scheme by Jordan, Farhi, and Shor, and it's similar in spirit to the methods that Milad Marvian talked about yesterday, except there's one important difference, which is that in Milad's talk, also the transverse field term was encoded. But here we can't do that because the repetition code would require an n-body product of sigma x terms, which of course is not available to us, at least not on the D-Wave machines, and not likely to be available anywhere, which is why Milad was talking about a completely different family of codes and not the simple repetition code. But this is something that we can do, and this is why I'm talking about it, because it's programmable, implementable, realizable on actual machines today. Okay, so a few quick theory facts about the scheme. It was analyzed in a number of papers, and Shunji Matsura recently wrote a very nice review paper about it. But here are some of the original literature. There's also a patent that recently came out of this work. So essentially the conclusion from the mean field theory analysis is that this scheme has a number of beneficial effects. It softens the closing of the gap, meaning the gap doesn't close as fast, typically. It lowers and narrows tunneling barriers, and it also reduces the effective temperature. So you can basically trade qubits for lower temperature. You can't reduce the temperature of your dilution fridge anymore, but you can achieve an effective temperature reduction by encoding qubits using this kind of scheme. And all this can be proven using a mean field analysis. But I won't say any more about the theory now. I want to present the empirical results. So before I go there, we have to recognize that once we do this encoding, we end up with a different logical graph. So here's the physical graph of the 2x. And if we do the QAC encoding, which groups 3 physical qubits plus 1 penalty qubit, we end up with the following logical graph. Every green circle now is a logical plus penalty qubit. So every green circle now represents 4 physical qubits. Every red circle, of course, is either a missing qubit or a missing coupler. So on the 2x, we ended up with a maximum of 236 functional logical qubits. And what we do is we consider the encoded Ising Hamiltonian, the same as I described before, with the same set of J's. And this logical problem, we then need to compare to the unprotected case, right, where we don't do the quantum annealing correction scheme. So one way to do that is to just consider this minor of the chimera graph and run it where now every green circle is a physical qubit, right? So we could let the machine solve this problem and, again, add noise to it like before. But this wouldn't be fair, this kind of comparison. Right? If I just run one copy of the problem, I'm not making a fair comparison because I gave the QAC scheme 4 qubits. Right? So I should equalize the resources. So really what we should do, because the QAC scheme uses 4 times as many qubits, we should really, rather than run the unprotected problem once, we should run it 4 times. Now we've equalized the resources. Right, now this comparison is fair. Run the unencoded problem 4 times and pick the best of the 4. All right, so we give the unencoded problem 4 chances to find the right answer. Now it's an apples to apples comparison where we use the same number of qubits in both cases, the encoded case and the unencoded case. Okay, so first just a snapshot of how the scheme performs. So this is the, oh, by the way, I should have said I call this scheme 4 copies without the penalty term, right? Without encoding into a repetition code. We just call this C for classical. This is just the classical repetition of 4 copies. So this scheme, where we pick the best of 4, the C scheme, here's what happens at size L equals 14 with 0% noise added. And this is all the 100 instances that we did for this choice of parameters. So what you find is that the success probability is kind of low to begin with, but actually the success probability is strictly 0. The machine never succeeds in finding the ground state for more than 90 of the instances. It only actually finds the ground state about 10 out of 100. That's without doing the QAC scheme. Now, when we introduce the QAC scheme, the situation improves a lot. All right, so now essentially all instances are solved, I think, except for 2 or 3. And the success probability is also increased. All right, so the scheme actually, as this combination of parameters demonstrates, it works to overcome these control errors. Of course, we don't want to just look at a particular combination of parameters. We'd like to do some kind of a scaling analysis. So first, let's look at it in terms of the fraction of instances where the success probability is higher with the scheme than without the scheme. Okay, so that's exactly this fraction as a function of size. And the different colors represent different noise. So going in this direction, we add more noise. And here, these are all the combinations we tried. Add 0 noise, 3%, 5%, 7%, 10%, 15%. So if the fraction of instances is larger than 0.5, then the scheme helps. If it's lower, then the QAC scheme hurts relative to doing the simple classical repetition. And you see that generally, as the problem gets bigger, we tend to go above this break-even line. And also, as the noise gets stronger, we tend to go above this break-even line. And in fact, for the largest noise level, adding 15%, it always is beneficial to use this scheme. Okay, so the scheme helps more as problem size and control noise grow. What about time to solution, our favorite metric? So here, time to solution is just a number of repetitions to find the solution at least once, with some probability. In this case, we're looking at the median. And so this is, again, the classical repetition scheme. And you see that some of these curves terminate. None of them actually goes all the way up to 16 because the ground state is simply never found. If we do the QAC scheme, the quantum annealing correction scheme, for all the way up to 7% added noise, there's always a solution found. Right? So the curves never terminate. And moreover, you can kind of eyeball that the scaling is better. Right? And again, we confirm that the effect is better the larger the problem size and also the larger the noise. So to make that more quantitative, let's look at the ratio of these scalings. So that's what this plot is. This is the ratio of the time to solution of the C scheme to the QAC scheme. So in other words, when the time to solution of QAC is smaller, QAC helps, right? So that's above the break-even line of 1 here, and below it hurts. And here again, as a function of problem size, you see that as we increase problem size, QAC tends to help. And for sufficiently large noise, again, noise increases in this direction. For sufficiently large noise, again, it helps. So this is in terms of the scaling. So not only do we improve the raw success probability, we also improve the actual scaling of the time to solution, which is really, really what we want, right? We want to get better scaling using some type of error correction. Okay. So now let's go back to the first doom plot that I showed you. So recall that if I had a classical computer and I just let it run brute force deterministic searching for the solution, it should never take it more than a time that scales like e to the L squared. And the depressing result without doing the annealing correction scheme was that the exponent here was greater than 2. So it's worse than classical deterministic. But now with the QAC scheme, if we do the same kind of data collapse of all the different noise results, they all collapse nicely onto a single curve, and the exponent now is fortunately less than 2. And by the way, there are error bars on these numbers, and within 2 sigma standard confidence, this is well below 2. Okay, so the nice conclusion from this technique is that error correction restores hope, in the sense that we are now definitely beating the classical deterministic scheme, and we absolutely want to be there. I'm not saying that this proves any kind of speed up relative to classical, but this absolutely proves a slowdown. Right? Whereas this gives us reason to believe that there could be a speed up. Okay, so to summarize, the quantum annealing correction scheme mitigates analog errors. It doesn't totally overcome them, but it mitigates them and improves the scaling relative to not doing it, even if you allow yourself majority voting on multiple copies of the same problem. There's absolutely reason to expect that better codes will improve these results. The code that I showed you here is the simplest, most naive, and least effective of all codes that could be tried. And finally, I want to make very clear that while these results, I think, are encouraging, they are far from being the Holy Grail. The Holy Grail would be something like an accuracy threshold theorem, like we have in the circuit model, where we have fault tolerance. There's no such thing currently for quantum annealing, and to me, that remains the biggest open question in this field. Thank you.
Thank you. In the last slide of the doom section, you said that, well, you used the phrase that this graph absolutely proves slowdown. And I wonder if you can go back to that last slide of the doom section, or maybe this is the exact same slide.
Yeah.
So I'm just trying to understand, in terms of the absolute proof of slowdown, there's a few things. You're looking for the exact solution, or you're okay with an approximate solution?
I'm looking for the ground state.
For the ground state. Yeah. In a lot of problems, we don't need the ground state. We just need a very good, a low energy, you know what I mean?
Of course.
So in that case...
That's a different metric. That's
a different metric?
That's a different story.
Okay, and apart from that, even if we're looking for the ground state exactly, what are we looking at here? I don't really understand. If you have you shown that the classical? I mean, this is a classical upper bound, but have you just shown the classical computer doing better than the annealer? Just
right. So in case I wasn't clear, so what the scaling result shows with the scaling exponent, right? It's double exponential scaling. What this double exponential scaling exponent shows is that if you, instead of using a quantum annealer, just put this on your laptop and let it run a brute force search for the optimal solution, it would be faster.
But this is just a computational complexity scaling. I mean, it's a formula for the cost. But if I have 1986 computer versus a 2010 computer, there's a difference in the speed. So
I'm interested in scaling, not interested in prefactors.
Okay, but you might be able to show that a classical computer actually is faster than the annealer. Just that would be an even stronger proof.
There's no question that a classical computer, the scaling of the classical computer would always be better than this, than this 2.07.
Okay.
Right? Yeah.
Hey, Daniel. Thanks. That was a thoroughly depressing beginning.
But now you're happy, right?
Yeah, exactly. I mean, I'm kind of in a similar position as Nikkei, which is that I don't really want to judge quantum annealing in the same way we wouldn't be judging NISC based on, why aren't they performing as well as fully error-corrected devices? Because the whole point is that we're learning about what quantum computers can do and realizing they have capabilities other than just ground state, obtaining ground states. But nonetheless, I mean, it's a fair point. Error correction is an absolutely important area of development. It's an important avenue that we should be pursuing in this field. I'm curious to know what opportunities lay ahead for Pegasus-like architectures now that we have sort of 3 layers of a chimera on top of one another. Have you looked at encoding schemes there?
Yeah. So first of all, again, both of your questions, I am not saying anything about approximate optimization. This is a result for strict optimization, right? And the story may very well be different, and I don't really know, for approximate optimization. So maybe for approximate optimization, we don't need error correction as badly as we need for strict optimization. Now, you're asking about Pegasus, and that I'm actually very hopeful about Pegasus because of the possibility of using much larger distance codes. So essentially, with Chimera, natively, you can only use a distance 3 code, which corrects 1 error, because of the structure of the unit cell. That's this plot where this plot, right? This is Chimera. Now with Pegasus, we should be able to use. I don't know exactly what the distance of the code is going to be, but I expect that it could be maybe as large as 7. And that is in the category of further improvement is expected with better codes. Now, there's another point that I think it's fair to make, which is that here we took the machine all the way up to very high artificially added noise levels, right, in order to extract this scaling. Of course, you don't in real life want to add noise. You will want to work with the intrinsic noise level. At the intrinsic noise levels, if that's the only thing you care about, that's this bottom curve here, well, up to size L equals 10 or so, actually you don't even want to do the quantum annealing correction scheme. Right? So if you reduce the intrinsic noise level, as you guys are doing, things, again, of course, are going to get better. But what is unmistakable is that as you increase the problem size, even at the intrinsic noise level, there comes a point where you do want to do error correction, and that's expected from the theory.
I'm interested in a bit more detail about the noise models you're using, because you might expect other kinds of noise than Gaussian errors to be important in this, and whether just the fact that you've got neighboring qubits with random errors on them rather than correlated is helping with this result in a way that we've got to think about a bit more carefully in terms of, or it might be that it's helping us, that just the fact that you've got 3 different qubits with essentially the same J's on them is helping cancel out the specification errors, which is what you were specifically after.
Yeah. So I think I detected 2 questions there. One was about the noise model, and the other one was basically what's the mechanism that makes this work, right? So as for the noise model, Gaussian noise on the control parameters is a pretty good model. Of course, it's not the only source. There's decoherence. And actually, the scheme was originally developed to deal with decoherence. And it does that, I think, does that pretty well as far as we can tell, because there is decoherence, and we are increasing the success probability. It's just that it's much harder to figure out exactly what's going on with decoherence, because it's not really a control knob that we have, like this adding Gaussian noise. As for the mechanism, I think we'd better discuss it afterwards. It's a long story. But essentially, I think your intuition was correct.